Hello everyone, let's get started. My name is David Talby. I'm from TGO, nowadays based in Seattle. And I'd like to talk about some of the things we've learned over the years about what happens after you take data science, AI, machine learning systems and put them in production. So we've been doing this for quite a few years. And one of the things I've noticed is that there's a lot of experience in how you monitor web services, REST APIs, applications, how you make sure they work well in production. They're monitored, they scale. There's relatively little knowledge about what happens with machine learning models once you put them in production. And we've noticed some pretty weird things that they do compared to traditional systems. So the first thing, and if there's only one thing you take from here that happens with machine learning models is this. Once you've trained the model, you've measured it, you optimize it, you did the hyperparameter optimization, you put it in production. At that point, it's performing the best it will ever perform. Because from that point, real life starts to happen, and it starts degrading. Okay, which means that if you just let it be and leave it on its own, within anywhere from 4 weeks, 4 months, maybe later if you're in luck, a model that had a 95% predictive accuracy is going to deteriorate to something that's as good as a coin toss, because life happens. And that's something that you definitely need to pay attention to and be prepared for before you go to production. So one of the best papers in this area, very easy reading, is from Google from about 3 years ago, and they surveyed basically what happens across tens of teams at Google that applied machine learning and AI models, and they came up with this title, and basically said, look, if in traditional teams, yes, you're in production, you're going to have like 10-15% that you have to devote to keeping your system running. Once you have a data science team, you might as well devote half or more of what the team is doing to just keeping the system where it is. And one of the main points that they noticed was really just the fact that the world changes. Okay, and we used to build basically systems like calculators or workflow management systems. As long as the business process is stable, the system works. Now we are really running, the day-to-day, in the case of Google, day-to-day, searches, recommenders, and as people's tastes change, you need to be able to change things very quickly. Here's one example that we encountered. About 3 years ago, we had to build a system that predicts which patients that are being discharged from a hospital will come back within 30 days. We had a huge amount of data. We had about half of the US population, the insured US population. We had billions of claims. We had very nice comprehensive views of people over time. And it seemed like a very straightforward supervised learning problem. We had 2 years worth of data, so I can take 18 months. I can see people going to hospitals. I can see them discharged. I can see who actually came back and who didn't. So I had more than enough training data that was accurate because this was based on billing data. And we said, okay, we fit a model, and we build a nice ensemble model which performed well. And then here's what happens once you put it in production. So basic model says, look, here's the patient details, how likely is this patient to come back? But then here are the problems that you start encountering. First of all, you have locality, right? So if there is an epidemic, the probability that I'll come back because of my pneumonia, so obviously depends on how many other people like me came back because of the same pneumonia. Okay, because if that happens, it means that in our hospital, in our city, we're just not giving the right kind of treatment, right kind of antibiotic. Okay, so there's those locality aspects that basically break the idea of deploying the same model everywhere. There is a seasonality, right? So the probability that my COPD, my asthma, my pneumonia, whatever may be the case, will come back is different whether I'm in the summer or the winter. Obviously. There's changes that actually happen within the population. And you take a look, the population of the city does not change as much to change the distribution of diseases. But what happens within a hospital, it's enough to move one doctor, one hotshot cardiologist or oncologist from one hospital to another, and you completely change the kind of patient, the distribution really of diseases you're going to see within those departments. You had 5 beds to the ER, which can be an overnight decision of one person. And you completely change the distribution of who comes to the ER, what they have, which means that your model, a lot of your priors are going to be completely broken. And what the doctors will see very quickly, and usually it's really within weeks, we see that the model started very high performing, really degrades to junk within a few weeks. The other critically important thing that most people don't think about in advance is the fact that you deploy the system changes the ecosystem, right? So you break your own models. Okay, so we're not trying to predict who is going to come back to the hospital and then run it as a scientific experiment to see if our model is correct, right? Once we deploy the model, the whole point is, look, if someone is at risk, we let the nurses know, and the discharge process for that person is different, right? So the whole point of our model is, yes, we put it in production, it comes with the software system, it comes with the business process, it changes what's going on, and inherently breaks your own model, okay? And that, that's very intentional. And then on top of that, you have all of these things happen at the same time, right? So it's very hard to even know which is which. Okay, and if you think seasonality is something, yes, you can probably model with some decent time series analysis. It's extremely hard to do in practice once you have all of these things combined. Okay, and what you need to do is something different. So in terms of how big of a problem you have, one thing to know about it is it does not depend as much on your algorithm. Okay, so it's not that a smarter machine learning algorithm will give you a more stable model. It depends on the problem, right? So if you're doing a voice detection for myself, for example, my voice is fairly stable, right? Our voices they change slowly as we age, but it's decently stable. Social preferences change on the order of usually weeks or months. And I mean, what kind of TV shows, movies, celebrities, news I would want to see, right? If you're within the e-commerce, web search, social recommendations, those areas. And if you're doing anything around cybersecurity, real-time bidding, advertising, automated trading in finance, then you're looking at multiple changes per day. Okay, and really the first thing you need to figure out is really where your model is on that spectrum. Okay, and based on that, what you need to do, you just need to put in the right machinery. Okay, so for something that are very stable, for example, I need to identify whether this image contains a cat or does not, which is a very stable thing, okay, although somewhat academic, then I'm probably good with just handcrafting, some neural network, and that's that. Okay, as I go to the right, as I go to real environments that change more rapidly, I need to start looking at active learning, passive learning, I need to automate master-challenger methods, and I really need to make sure that machinery is actually there. And really the difference is here between, are you doing something academic or actually building a product? And really what I've seen time after time is that these models, they do not degrade over a 2-year period. They degrade over weeks. Okay, so if you have a customer, they're going to come back to you, within the same invoice asking questions. So it's definitely something worth paying attention to and making sure that on one hand you do not over-engineer, on the other hand you do not, you don't downplay the problem. So that's one thing. The second thing that happens, partly because of the first problem we have, is this. So, software used to be, it used to be really cool because I can write my software once and I can sell the same CD, a billion times and make money of it. So, that was fun while it lasted. Now we're in a different world, and really what we're seeing all over the industry is that in practice models do not really generalize as well as you think. Which is why, if you think about it, in the open source community, there's a lot of infrastructure that's open source. There's a lot of algorithms that are being open source. There are very few models that are being open sourced. Okay, and the reason is very simple. Those models, they just do not work as well. Right? So if I give you a model that I train specifically for image recognition, for language, for patient identification, most likely if you try it on your own population, you're going to get poor results. Okay, which means that what you need to do is you need to reuse really the modeling pipeline, so maybe the infrastructure, the modeling pipeline, the feature engineering, but you will need to train your own model. And one great example here is actually on readmission prediction, just the same simple supervised problem that we just walked through. These 3 academic papers and models were pretty much the state of the art about 3 years ago. Each one of them was trained based on patients from a specific city in North America, and when the NHS in the United Kingdom looked at the model, they came back with this paper that said basically they got AUC numbers of around 0.53, 0.54, which are really just above a coin toss in terms of just how poorly those models have been. Okay, because if you take, for example, the LACE index, which is still the most widely used readmissions sort of score in North America. It was trained on, on 11 hospitals in Ontario, mostly on middle-aged women. Okay, so even not all the wards within the hospital. So obviously, if you take it to an older UK population, you're looking at, you're just looking at completely different people, completely different diseases, completely different age groups, right? So really, most of what you trained on does not apply to where the model is actually used, and you get what you'd expect. Which is really, it's not surprising, other than the fact that when people order software projects, when people expect software projects to deliver, it should be pretty basic by now. I roll the spec, you build the project, we had tests, we had sign-off. Okay, that works when you can write the spec and the requirements are basically stable. Okay, then do not work when you want this thing to actually make inferences on a population it has not seen before. So it's something to keep in mind. As with anything, you can kind of say, okay, these are population. Look, obviously, if you're dealing with 70-year-old men versus middle-aged women, they're very different in what happens to them. But here's another example. That was a project we did where we looked at free text radiology notes, and the goal was to do some NLP, machine learning, and understand really what was the procedure. Okay, so read the note of my CT and come say, oh, this was a CT of the leg, because the person had a traffic accident. Okay, that was the goal. And here's some of the example. We trained the model on one customer. We figured, really we thought we had it made because those notes are very standardized, they're templatized, the radiologists go to the same school. And what we got are, really these kinds of graphs where you go from over 90% recall to over 10% recall. Okay, which in practical terms means that, instead of in 9 out of 10 times actually having a diagnosis, now in 9 out of 10 times there's nothing, right? It's like 90% of the time the thing is completely useless. And when it finds something, it went from 95% correct to 50% correct. Okay, which, now if I'm the person using this UI, it means that I have to read anyway, right? Because half the time you're wrong, right? So the system might as well just not exist. Okay, and we did found that really the goal changed from, what is the accuracy to how fast do we get to a high accuracy in a new client. Okay, and became much more an engineering project on building that pipeline, right? That modeling pipeline, training pipeline, and measurement pipeline. There's one best practice, the Google paper mentions it, I've seen it work very well as well, really to know how much of a problem you have, which is as follows. If you have a model and you want to get some intuition about how well it may apply in production, one thing you can do is really look at the distribution of classes on your training data. So what did I train this on? Look at the distribution that you're classifying into in production and just compare the two distributions. Once you start seeing a difference, it probably means that you need to retrain a model or train a localized model. Okay, so this is one thing that's really simple. All you have to do is count, right? Count what was the distribution when you trained, what was the distribution in production, and you know really how fast your model is probably degrading, right? How much your in production performance and accuracy is degrading. So that's one metric that works really well. In general, what we are saying that just as we build software over the years, we added we had server monitoring and then we added application monitoring. Now we're beginning to add this new level of monitoring to really understand and be able to explain how well those systems do in practice. Okay, so if we thought we were in trouble so far, really we're just getting started because sometimes you're not even able to build a high-performing model before we go to production. And for us, it happens very often. There are two primary use cases. One use case is what's called adversarial learning. Okay, and adversarial learning are all learning scenarios that you basically encounter when you do fraud detection. So we did a lot of fraud detection for healthcare, for basically financial fraud. But it happens, if you're doing any kind of cybersecurity work, any kind of really financial risk analysis. Okay, and because what you were seeing, so in classical supervised training, you train me, you send me examples, I tell you, is it class 0, class 1, you tell me whether I'm right or wrong, and as you give more examples, I build my model and I try to get better. In adversarial learning, as I get better, basically you change the rules, you change the classes. Okay, because you try to make sure that I don't successfully learn. Okay, which really what happens when you're doing fraud, if you have a specific, tax evasion scheme, and I start getting really good about catching you, you're not going to go away. You're not going to give up. You're going to change the scheme. Okay, in the case of healthcare, really not a day goes by you don't uncover a new type of scam or a new type of scheme that people are doing. It's the same with tax fraud. It's the same with social security fraud. And if you're in the cybersecurity space, you know that it's much more than once a day, right? It's many, many times per day, which means that you cannot train a model and then put it in production and have it get stuff. The work is in production, right? So the fight happens operationally. Another use case that's very common in this case is anytime that you have a semi-supervised learning problem. So that's a project we worked on a couple of years ago. We're looking for insider threat, which is a huge problem for banks. In the UK, banks sort of routinely pay the majority of the revenue back as fines. And in general, we're talking about here, but really catching things like political contributions, collusion, corruption, breaking Chinese wall, money laundering, terrorism funding, lots of interesting activities that people try to do. And it's very hard to really detect when something is right, something is wrong. Right? The more regulation you put on it, the more really you drive people, mostly the poor people outside of the banking system altogether. And it's a semi-supervised learning because here are the fundamentals. So we had transactions and we had all the communications that traders did, right? Because once you become a trader, basically, you sign up that all of this is essentially public. So here are the three core issues with this problem. First of all, this was the number of also good messages. Okay, so 1 out of 1 million message were what the humans would classify as suspect or a true positive. Okay, if that's your number, no algorithm, no classifier in the world will beat the trivial classifier, which is just say that everything is good, right? All of them are good, and this is classified with 6 nines of correctness, so the whole approach does not work, right? So you cannot really build a classifier. You're trying to build some kind of rank here that tells you who is more suspect and show it to humans and get some feedback as you go. The other problem you have is that there's no training data. Okay, there are only several thousand cases in total in history. Okay, each one of them may be $100 million, $5 billion fines, but there are very few cases. And it takes several months really to investigate a case. I mean, you cannot crowdsource getting more training data, right? You need forensic accountants and lawyers to just argue for months whether there even was a crime. Okay, and if you had that problem solved, the other problem was really, this is the number of schemes that we started with. Okay, but the problem is that, every time someone gets caught, right, so we gather all of us into a room and come and say, look, we just caught someone, here's exactly what he did, and if you're a bad guy, you're sitting in the audience, you take notes and you try something else. Okay, what this means is that when you have a system like this, you cannot train a classifier and come and say, okay, let's run it in production, see who we catch. Okay, what you really need to do is, okay, we go to production, we start generating some suspects, we get feedback from the human fraud investigators, okay, and the system learns as it goes, right, and we try to maintain some balance. Okay, what this means is you, as project leaders or project managers, product managers, whatever may be the case, you need to explain to your customers that your accuracy or performance the day you go to production is going to be the lowest it will ever be, okay, which is very counterintuitive to people, right? It means, look, first you sign off, then we start seeing if the thing works. Okay, but that's really the only way to do it. That leads me to my last point, which is also something that's very different really between data science, machine learning, AI projects, and so classic software engineering projects. Really, the fun begins after you've already gone into production. And that's very different, especially for people who are used to building teams, managing projects, deploying products, software products, classic software products. Because in classic software, here's how we do it, right? I need my best people at the beginning where I'm choosing really the hardest to change. I'm making the hardest to change decision. I'm choosing programming language. I'm choosing the platforms. I'm choosing my key dependencies, right? Then when I'm starting to write the code, I want my best coders because I'm building the framework, right? This is the most delicate code. The things will impact performance, memory use, security, right? And then once the framework is in place, they can add more people because now we're just adding more screens, more business logic, but there's a little less you can screw up. First time I go to production, it's a very big hand-holding deal, and then I send it to ops, right? And and that's that, right? And by that, my top people have already moved on to the next products, right? And that's how we build software, right? Because the biggest risk is at the beginning. When you're doing data science projects, I mean, it's really almost the reverse, right? So building a model. So let's say here's a set of CT images, right? And now I need to build a predictive model that tries to identify breast cancer, right? Is this cancer or not? So I'm building some, doing a grand deep learning exercise. Nowadays, this is almost a homework exercise. Right, it's like, yeah, we have the data, you have a whole bunch of open source libraries, you can do it, there are lots of examples, lots of blog posts, online courses. Anyone can gather within 2 or 3 months. Okay, now if you want to actually put it in production, make sure it actually works, right? You actually have a service, you have a server, you're doing the measurements, you know how well you're doing. That does require more skill and also a lot more experience, okay, because very few people actually done it. If you're moving forward and you get to a moment where you want to do A/B testing or multivariate A/B testing on a daily basis, that's extremely hard to do. Okay, most people, most teams, even the largest companies, if you look it up, Google, Amazon, Microsoft, I've been on those teams. They take 5 years and have lots of lessons learned about all the measurements they screwed up. I think Facebook just 3 months ago was still fixing measurements, right, on some of their internal metrics that they publish to advertisers, because it's extremely hard to do in a real setting. And if you're trying to do really automated learning in production, okay, so if you're really doing cybersecurity and instead of having teams of people, you want you want an AI system. An AI system is a system that really learns in production without without people. There definitely are those systems, but now you have very few people in the world who actually do that. Okay, so that's a big difference in terms of how you plan projects and how you plan your teams as well. So overall, in terms of what we spoke about, that's the main message, right? So when we did software engineering, it took us 40 years to decide software engineering is actually not like civil engineering or mechanical engineering, so we should not do pure waterfall as the end all be all. Now what we're seeing much faster, when you're doing machine learning, you're doing data science. Also you have some fundamental changes that are different from really classic software engineering, classic software deployment. The first thing it means that when you build teams, when you build products, you need to set expectations differently, right, with your customers. Okay, here's what's going to happen before we deploy, here's what's going to happen afterwards, here are the things you should care about. When you talk with your people, in terms of career development, when do you need them on your team? When is it going to be interesting, when is it not going to be interesting? It's different than in other projects, right? You should know it, you should set those expectations. And the other piece is look, the good thing here is that really we are changing, the reason this happens is because we are changing what we do, right? So when we used to build a loan processing system within a bank, right? The system did not process loans. The system managed the workflow, and people decided what's going to happen with loans, who's going to get them, at what, and they just really we digitized the paper forms, right? This was the first 20 years of that. Now, if you're doing banking, the system decides who gets a loan, right? Not the person. The system decides what the price is going to be, so what are the interest rates. The system decides who to promote to and who to market to, right? The people are the nice interface, right? So when you go into the branch, you still talk to a person, but they don't make the decisions anymore, right? The same thing, if you're doing real commerce or e-commerce, right? Now we have computer systems who do merchandising and do pricing and do promotions, right? And do buying, right? So we're actually running the business. Okay, when you're actually running the business, now you care, it's not just the workflow in the business process. Now you care about whether it's a weekend, right? Whether, whether it's hot or it's cold today, right? What are people's preferences? Where are they coming from? Who exactly and what kind of people are walking into the store today, right? What kind of promotions my competitors are running? So, we're in a much more dynamic environment, right? And really the main thing to pay attention to, especially, if you have a product, you have a system, right? And most of your time you'll spend with that system in production, right? And that's your responsibility. On one hand, it's really fun because you're actually changing your organization, changing the system. You get to a point where you are the one running the show, but you absolutely need to know it's going to be very different from the way other projects, software projects have been run. So that's what I want to say. Thank you very much.